Okay, so maybe we should start. So let me begin with a clarification from last time, because I was asked a question and I realized I might not have made myself clear, so I'll begin with that. So here is the statement that I claim I have proved using the heuristic that we talked about last time of computing the tangent space to Zariski closed subspaces or Zariski closed spaces. Or Zariski closed subgroup. So the tangent space, so V is a finite dimensional K algebra over a field K. The tangent space to ought V at the identity is der V. Okay. So the way so if you recall, I wrote identity plus epsilon x, where x denotes an element of the tangent space at the identity, and we wrote down the condition that this be an automorphism. Okay. And then obtained that x must be a derivation. Okay. Now that condition goes both ways. If x is a derivation, you can work backwards and show that this is a automorphism. So there is, once you see what to do, this is really very almost a trivial calculation. Okay. So then I started saying conversely you can do something, and that might have confused you. Confused in the sense that for this part, the proof is complete. It's just a couple of lines that we wrote down last time. Just write down the fact that this is, if you write down the condition that this is an automorphism, you will see that x must be a derivation, and if x is a derivation, then this will be a automorphism, easily checked. Okay. So this is easy to prove using the heuristic. Okay. And conversely, I said you can compute the exponential of a nilpotent derivation. That is not necessary for this, but we just did it. Nevertheless, we went ahead and did it because it's an interesting calculation in its own right. But for this itself, you don't need that. Okay. That's the first comment. And towards the end, I was a little confused myself. So let me give you exactly what I want to say. This is slightly, just a wee bit more general than what is in Humphreys. Okay. So let me give that as an exercise. So I think I had 6 last time. So this is, I'll call it exercise number 7. So V finite dimensional K algebra, characteristic of K, let's assume to be 0. So der V is the set of derivations of V is invariant for the adjoint action of ought V on end V. So adjoint action, so if adjoint action means you take a matrix here X or a linear transformation, how does an element of ought V act on end V? G acts on X by Gx G inverse. That's the definition of adjoint action, and this is very easy to check, but it's an important fact. Okay. Okay. Now suppose D is a nilpotent derivation. Okay. Then, as we have seen last time, then we've seen, exp of D makes sense and belongs to ought V, right? That's what we That's the calculation, that's one of the calculations we did last time. So it makes sense to ask the following question. So how does xd, if I take the adjoint action, so add of xd, which is.
I'm sorry, suppose you take the adjoint action of all of G and D, then you must get all of it. Invariant sitting inside NP.
Yes, yeah, that's correct. Yeah. So you could take the adjoint action of this on d prime, where d prime is a derivation. So I take this, which is an element of Autvy. Autvy acts on derivations. So I could ask, take the adjoint, which is nothing but, if you want to expand it, you can do it like this. You can just verify that the inverse of exponential of d is exponential of minus d. Okay, you can do that. So what is this equal to? This is equal to exp of add d on d prime. This is the formula. So this is the exercise you have to prove. So prove that this is the case. Now notice this is related to what Upendra was mentioning in the morning. If d is a nilpotent derivation on V, add d. So here is some comments. D nilpotent implies, now add d acts on der V, right? If you give me a derivation, then d acts by, d, the commutator of d with that derivation is again a derivation. Commutator of two derivations is a derivation. Now what you write add as left multiplication by d minus right multiplication by d, and those two commute and so on. Using that, you can show you that if d is a nilpotent endomorphism of V, add of d will be a nilpotent endomorphism on the endomorphism space. So d is nilpotent means add of d is nilpotent. Okay, nilpotent actually on end of V if you want, but in particular on der V. Okay, so it makes sense to talk about exponential of this add. Okay, and so prove this formula. Again, this is not at all difficult. This is just a few lines of basic algebra, just writing it down. But it's good to write this down in the most compact way, because that means to write it down in the compact way itself, you will need to understand and make sure that you have kept the concepts straight. You've got the concepts straight.
So over there, d is nilpotent.
D is nilpotent. D prime, there is no assumption on d prime. Yeah. So I've assumed this. Suppose d is a nilpotent derivation.
So V groups is generally true. I mean, d nilpotent or not?
Possibly, yeah, possibly. In any case, I mean, so this is a very simple, there's nothing much to the exercise itself except understanding what it means. Okay. Okay. Now, let's see. One more comment before I go on. So we talked about Jordan decomposition. I did yesterday, and maybe I was a little cavalier in saying I had assumed that. Today morning, Upendra was much more careful. He was assuming algebraically closed field. I didn't mention any condition on the field. So that's not correct. You need at least K to be a perfect field. So needs, assume K perfect. Or if you don't know what perfect means, never mind. Just assume algebraically closed field. Okay? But you will need, you can't do this over an arbitrary field, as I might have implied by what I said yesterday. So I want to correct myself and say that for Jordan decomposition, you need some assumption on the field. If it's comfortable, I mean, if you are happy with it, just assume the field is algebraically closed and be done with it. Or if it's characteristic 0, it's perfect. So in characteristic 0, there is no problem, which is most of the, very often we are over C. Okay, but it's also nice to think about some of these things in other characteristics or other fields. It's not a pathology at all. It's interesting, but you may choose, if on a first pass, to ignore that and just assume the field to be the complex numbers. Okay. So now let's get back to representation theory of SL2C. That's what we were doing. So finite dimensional. So let me start here. Finite dimensional representation theory of SL2C. And one thing that may not be, I want to say in the beginning, because I want to emphasize this, I'll say it again because it bears repetition, is although it may not be obvious, there is a very strong connection between what you know about finite group representation theory over, say, over the complex numbers and this, although it may not be evident at first sight. So you should, it's good to ask yourself, it's good to keep, ask yourself, oh, is this statement true if you're working over, I mean, try to go to see, to match what you know between this and what you know from finite groups over complex numbers. Okay, so there is yeah.
X and D means this operator plus identity plus this operator plus.
See, no, let's think like this. D is an element of the Lie algebra derivative. Add D is therefore a derivation of this Lie algebra, and it is nilpotent. So it is a nilpotent derivation on a certain algebra. So I can take its exponential, which will be an automorphism of that algebra. Namely, in this case, it will be an automorphism of der V. Yeah. So that's. I'm saying this very boldly and it's being recorded. So I hope, I mean, so this. So for example, the first statement that we made yesterday, that, so that there is that give, so I might not write this 2. So now this is lecture 2. Give an example of a finite dimensional Lie algebra and a finite dimensional representation V, which is not completely reducible. Okay, this is not a very difficult exercise. Maybe you know the example. I mean, but it's important to do this. Okay, so complete reducibility, what does this mean? You take any module, or, so we will use the word module representation interchangeably. Okay, so any SL2 module is a direct sum of simple or what is the same irreducible modules. Okay. Now, simple modules, so you can always find simple submodules just by induction on the dimension. Okay. If this is not simple, then it must have a proper non-zero submodule. You go there, and if that is not simple, then it must have a proper subsets, and so on. You can always find a simple submodule. That's not a problem, because you are working over a finite dimensional object to begin with. Okay. The problem is that it may not have a complement. Let's see. Okay. It may not. There may not be another module such that invariant for this G such that the direct sum of those two will give you the whole module. That's the problem. Okay. But in the morning today we saw, even went sort of revised our proof of complete reducibility for finite groups over fields of characteristic 0. You basically you do this by some averaging. Well, we didn't quite see the proof maybe, but we saw the technique that underlies it, namely the averaging technique. Okay. Now, so here is, so at least by analogy the result is true. You could ask yourself whether a proof can be given which is analogous. Okay. And indeed that is true, but it's outside the scope of this school, in the sense that you have to do this over compact groups, and then you can use integration instead of for averaging, and then it works exactly like the finite group situation. Okay. So the point is, in fact, the proof for finite groups also works in this situation, but we will, for now, you just take that as something, store it away in your mind so you can look it up later sometime, but we are not going to do that proof. Okay. I might give you a proof tomorrow, next time, or an idea of a proof, or maybe even today, which is more, which is a different, which is where the analogy, if it exists at all, is much more lies beneath the surface. In any case, this is the statement. Okay, so that every SL2 module is a sum of irreducible modules. So we are reduced to understanding what the irreducible modules are and how many there are and what their structures is. Okay? And like yesterday, I'll put it down here that in addition to complete reducibility, you have the following thing, that uniqueness of decomposition. And like I was mentioning yesterday, this is no big deal. If you have this is true in great generality, if you have a module which is a sum of simple modules, then it is uniquely a sum of, I mean, there is this unique decomposition holds in that generality. Okay. So we are not going to worry about that, but in any case, the good news is that in this particular case, you can prove uniqueness of decomposition by, I'll write this here, linear independence of irreducible characters. Now that should ring a bell, right? You have irreducible characters in finite groups and they are linearly independent. Okay? And that will give you that the decomposition is unique. Okay? So it is true in very abstract, in a very abstract setting, but you can prove it using much more, it's much more concretely in this situation. Okay? And the last two items I mentioned was, so then the question becomes, what are how many irreducible modules are there? And the answer is the set is parameterized by the non-negative integers. Okay. So there exists, so the irreducible are in correspondence with one-to-one correspondence with non-negative integers. So if I denote a non-negative integer by a symbol lambda, the corresponding irreducible will denote by V lambda. And finally, I had said that dimension of V lambda will turn out to be lambda plus 1. Okay. So, for example, when lambda is 0, dimension of is 1. Okay. So what is V sub 0? Yeah, it's a complex. And what is the action? Trivial action. That is, every element of the Lie algebra acts as 0. Okay. So V0 we see is the trivial module. And you want to guess what V1 might be and what V2 might be? I claim you know these. So V0 is trivial. V1. Exterior power of what? But of. So what is it? So what is V1? Go ahead and say it. On C2, 2 cross 1 matrices. Yeah, okay. So this is isomorphic to, you can say 2 cross 1 matrices. And SL2 acts on this by matrix multiplication on the left. Okay. And how about you? I think you know also this. At least it was mentioned as one of the very important representations. Acts on itself. Yeah. So, and why is that an irreducible module? Because it's a simple Lie algebra, which means it's an irreducible module. So it must occur in this list, and it has dimension 3, so it better be V2. Okay. So this is SL2 adjoint. Okay. Now the question is, what are V3, V4, V5, V6, right? Okay. So among the things that we will answer today will be that. Okay, I'll repeat from what I said yesterday, that you should look for, I mean, these things are, we have these two in great generality. This is true for all complex semi-simple Lie algebras. It's one of the basic theorems of the subject due to while. It's Weil's completely reducible. Okay. Uniqueness of decomposition, I said, holds very generally, but this proof works also in any context, but this proof works also for any complex semi-simple Lie algebra, not just for SL2C. Okay. Now here you have a similar, maybe if you go to a more complex semi-simple Lie algebra, then this parameterization will be not by non-negative integers, but still a discrete set, a set of integral points in a certain cone or something like this, okay, which will be part of what we will study. Okay. And then again there will be some theorems about the structure of V lambda, such as what its dimension might be, what its character might be. That is, okay. So this formula, like I was saying last time, is a special case of what is known as the Weil dimension formula, which is an important formula. So it's a special, okay. Now, now we are in a very happy situation about in studying this subject. Not only is it a baby version of what we want to study, so it is shorn of all the technicalities. So, but it also has retains all the essential features. Okay, that's a very happy situation. So you can sort of understand this and generalize by analogy with great confidence. Okay? That's one good thing. The other thing is this, you can use this not just as a not just as an analogy, but actually in proving things about bigger Lie algebras. You can use these theorems themselves. Okay? So it's a very good and happy situation. So so the general, if somebody asks you about complex semisimple Lie algebras, tells you a statement, then one way to start thinking about it is, what does it mean for SL2? Or that would be the first thing one could ask. And if you can't answer it there, then that means you really have to think. Okay? But very often you can answer it, and then that's then you can bootstrap yourself upwards. Okay. So one of the models we learned from last time was, when you think Lie algebras, you should think derivations. Okay? So I'll give you a set of representations of this Lie algebra, SL2. Okay? And so where should we look for the representing objects? They are represented as derivations. So I should look for good derivations. So here is a set of derivations. So I take P to be polynomial ring C U V in two variables. Commuting variables. Okay. And then I take X to be U del by del V, H to be U del by del U minus V del by del V, and Y to be V del by del U. Okay. Now these are derivations of that algebra. So what is a derivation? A derivation is a linear map which satisfies the Leibniz rule. But we know the Leibniz rule holds for partial derivatives. So, and you have some multiplication by some functions in front, but that doesn't change. That still is a derivation. So these are derivations. Okay? So these elements live in the Lie algebra of derivations of this polynomial ring. Right? Okay. Now I am saying, look here, there is a copy of SL2 in this. I am sending X, so I make X act like this, H acts like this, and Y act like this. Okay? Now to make sure that this is indeed an action, I have to check the structure, that the structure constants are okay. I mean, this indeed is a representation, and that's an easy calculation. I won't do this. Okay? So gives a representation of SL2 on P. Okay. Now notice how is the X acting? It is del by del V times U. So it is reducing the V degree, kicking up the U degree, but the degree is preserved. How is H acting? Again, it preserves the degree. So is Y. So which means each degree piece is an invariant. And what are the dimensions? This constant is one dimensional, the linear things is two dimensional, and the degree D things are D plus one dimensional. So what's the conclusion? That these are indeed the V lambdas. That's the claim. So I've told you what the V lambdas are. Now of course we have to prove that they're irreducible, but that's also very easy, as I'll tell you. Okay. So, so PD is equal to homogeneous polynomials of degree D is SL2 invariant. Okay. And here is exercise 2.2. Show R. That's not so very difficult. So if it has a proper submodule, take a polynomial and then hit it with one of these, maybe x. So you will go up, you will decrease the v degree and keep going up, and you can, so you will kill off many terms and try to keep a single term, and and then backwards. You just going up and going down using these operators. This is a very easy exercise to do. So I'll leave that as an exercise. Okay. Okay. So they are irreducible and they are pairwise non-isomorphic because their dimensions are different. Okay. So we have produced the V lambda. Okay. So we know what we have one, we have one model for these V lambda. Okay. What happens is, in general, is if you might be given a representation, and then to decide how it splits as a sum of irreducible representations may not be always easy to do. It's a different story altogether. But at least we have one model. We know all the irreducibles, how they explicitly look. Okay. 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 Now let's go about proving that these are all the irreducibles. Okay. And what see, what else did I say? And I will talk about characters. Okay, what do we mean by character, and how characters help us understand these SL2 modules, and that actually holds generally for semisimple Lie algebras. Okay. So just like characters help us understand representations for finite groups over complex numbers, the same thing holds here too. Okay. The character determines the representation. Okay. So we'll now make a sequence of very pleasant, simple observations, and in the end we'll have proved all that we want to prove. Okay. So let me start on that. So I wanted to, well, I'm thinking of giving you another exercise here, but I'll resist. Okay. So here is the, so I call action of H, action on eigenvectors of H. Highest weight vectors. this is a term that you will hear very often, every day, several times from now on. So that's the so here is the situation. I am given an SL2 module V, finite dimension. So V finite dimensional SL2 module. So I want to start analyzing it. Okay. So I look at how H acts, and we are over the complex numbers. So every operator is bound to have an eigenvalue. Okay. So first thing I do is I look at I look at a particular eigenvector for H. So let V be in V such that HV equals lambda V. Okay, it is some eigenvector. I mean, I'll use lambda like that, but that lambda is not to be confused with this lambda. Okay. So such a V and lambda exist, right? Because we are over the complex numbers, and H is a linear operator on this space. Okay. Then if I act X on V, it's a simple and pleasant calculation, tells you that this is also an eigenvector for H, but with eigenvalue lambda plus 2. So this is equal to lambda plus 2 of xv, and this is an easy calculation. See, you will write hxv. How will you write it? This is hx is, you will write it as hx commutator plus xh. Okay, but hx is 2x, so use that and you will see this immediately. Okay, and similarly with this is so what does this tell us? If I take the space of all eigenvectors for H, that's an invariant submodule. Okay, so thus the space of all eigenvectors for H is an invariant submodule. And if V is irreducible, then V must be this space of all eigenvectors for H must be all of V, which means H acts. So if V is irreducible, then we conclude that H acts semi-simply. Okay, now let's also go on and analyze, these are very simple observations, but put together they give us what we want. So here is another thing we can do. So let V say this is eigenvector for H. So this is such that HV is equal to lambda V. Then I take xv, x square V, suppose I do this. So from the first observation there, what can I conclude? V is an eigenvector by assumption. Xv is an eigenvector for H again with eigenvalue lambda plus 2. X square V is eigenvector for eigenvalue lambda plus 4 and so on. Okay. Now, therefore, they are linearly independent if they are non-zero. Okay. So, if these are linearly independent if x and v not equal to 0, because they belong to different eigenspaces for H. I mean, H is H is diagonalizable. That is, V is generated by a set of eigenvectors. V has a set of eigenvectors for H. Yeah. Sorry, the word semi-simple is used in so many senses, but always meaning, you know, in the end you can always, I think, reconcile all the meanings, but it's not always, yeah. So the word semi-simple is used. Yes, yeah, that's a semi-simple module. Here it means that actually here what it means is if you make that V into a KT module where T acts like this operator, then that V is semi-simple for that module. In that sense it is correct. Okay, so we have observed something else. So what does this mean? If I start with a certain V, which is an eigenvector for H, which I am assured that it exists because I have assumed my base field is complex numbers, hit it with x, hit it with x square and so on, keep going. If this continues, I will get an infinite dimensional module. That cannot be because I have assumed V is a finite dimensional module. So I will, after some time, get something that x will kill. Okay. So conclusion is that there exists eigenvector, V in V such that HV equals lambda V for some lambda and xv equal to 0. Okay. Such a thing is called a highest weight vector. Okay. The word weight refers to the eigenvalue for H. Okay. And the word highest is a little, the meaning of why this highest will become clear as the course goes on. Okay. So, but for the moment take that as some kind of a whimsical terminology if you wish, and let's go on. So this is called such a vector is called a highest weight vector. So what we have proved therefore is that highest weight vectors do exist. Okay. That's what we have proved. X raised to the n v will be 0 therefore. So I can look at x raised to the n minus 1 v. The first time it is 0, I look at the previous one and that will give me the, I replace v by that xn minus v and lambda by that corresponding eigenvalue. Yeah, that's what I mean. So here is another exercise. Show that x and y act nilpotently on V. Okay. If you use theorems that, okay, so let me mention here that there is something called the preservation of Jordan decomposition that Upendra will start talking about, and I will continue. What it says is the following. If you have a semi-simple Lie algebra, mind you, if you have this makes sense only over a semi-simple Lie algebra. So if you have this does not work over an arbitrary Lie algebra. First you have to keep that in mind. Okay. So if you have a semi-simple Lie algebra, then so you can start analyzing elements in this semi-simple Lie algebra. You can call them, they are called semi-simple or nilpotent, depending upon whether for the adjoint action the corresponding operators are either semi-simple or nilpotent. Okay. Now let us look at this. How does the adjoint action of H look? H and Y are eigenvectors for the adjoint action, because Hx is 2x, Hh is 0, Hy is minus 2y. So it's diagonalizable. So it's a semi-simple, add H is a semi-simple operator on SL2. Okay. What about add of x? Add of x is on itself is 0. On H it gives me some multiple of x. So if I act it again, it becomes 0. On Y it gives me H, and then if I act it again, it gives me some multiple of x, and then if I act it again, it gives me 0. So it's nilpotent. Similarly, Y will be nilpotent. Okay. And the theorem says that if in a semi-simple Lie algebra an element is semi-simple for the adjoint action or nilpotent for the adjoint action, then for any representation that the semi-simple ones will continue to be semi-simple, the nilpotent ones will continue to act nilpotently. So if you use that theorem, there is nothing there or here. Okay. So the point in
this is irreducible.
Which one? No, I am not assuming. No, I am not. V is finite dimensional semi-simple module, and then if V is irreducible, this was a aside. So at the moment, I am not assuming V is irreducible.
So V is not spanned by, V is not eigenspace.
No, I am not assuming that. So this was okay. So maybe I was not clear. I am working only under this assumption. This was an aside. So put that in brackets. At the moment, I am not assuming V is irreducible.
I mean, for irreducible, just follows from that first line.
Why is that? No, we could have many, many more vectors.
I know, but if V was spanned by eigenvectors of x of H, then that calculation is, because HV equal to lambda V implies that Xn V is 0 or something. I thought that's what you were.
No, sorry, I don't follow. So okay, so let's see. So I am assuming V is a finite dimensional module. Okay. So all I am saying is that there, first point I have made is that there exists some vector which is an eigenvector for H. So that's trivial because we are working over the complex numbers. Okay. Now the second observation using these two is that look at the set of eigenvectors for H. Maybe that's the whole space, maybe that's a smaller subspace. We don't care. We don't know at the moment. Okay. Eventually it will turn out to be the whole space. Okay. But at the moment we don't know that. Okay. So that subspace is invariant for the Lie algebra. So that's a submodule. That's all we have said. For the moment, forget that last line. Okay. Now continuing, we have said that there exists a highest weight vector, which means a vector which is an eigenvector for H, in addition is killed by X. That is by using this argument. Okay? Because otherwise you can keep on going. Right? It must stop.
So therefore X acts nilpotently on the eigenspace of H.
X acts nilpotently on the correct. Yes, yes.
And so does Y.
So does Y. Correct. Correct.
I thought that was the solution to your exercise.
Well, okay. Now I understand where you're coming from. Correct. But I'm not assuming V is irreducible. Okay. But then you have given the exercise because you can factor, you can take a Jordan-Holder series and on every quotient it acts nilpotently and therefore it acts nilpotently. That's the solution to the exercise. Yeah, thank you. Correct. So the solution also to the exercise has been given. Okay. Okay. Okay, now so let V be a highest weight vector.
I'm sorry, so there's similarly a highest weight vector for y also.
That's called a lowest weight vector, because somehow the h acting on that will keep going down, right? Yeah. So yes, you could develop the theory with lowest weight vectors and y in place of x. But, yeah. No, we are not assuming V is irreducible. No. Yeah, that's the. If V were irreducible, yes, this would be done by what Shiva just said. Yeah, but I am telling you that it does not matter, because action, if it acts nilpotently on a submodule and a quotient module, then it acts nilpotently. So essentially, you can reduce to the irreducible case. Okay, so that's the solution to the exercise. Yeah, the point is I am not assuming V is irreducible, and you should not use any theorem. You should do it bare hands. Yeah, that's the point. If you use something, that's what. If you use the theorem of Jordan, the preservation of Jordan decomposition. Yeah, I'm only saying x. So, but if you use the preservation for Jordan decomposition, since x and y act nilpotently clearly on SL2, they continue to act nilpotently on any finite dimensional module V, and therefore you would be done. Okay, so. Okay. The word Jordan. Okay. The word Jordan. The word Jordan is confused. No, I said without using the preservation of Jordan decomposition in semisimple Lie algebras. Okay. Yes, you need to, at least the way I am thinking, you need to use Jordan Holder chain. There also there is a Jordan, but yeah, good point. Yeah. I think it's the same Jordan, right? Okay, so let V be a highest weight vector. So we are assured now that this exists. Okay, now let's start analyzing a bit more, and we will get very soon. We are almost finished. Okay, like I said, it's a very happy situation. So let's write V, YV. Now I use divided power notation. Okay, and I think the Humphreys doesn't, but I urge you to use the, in spite of what Humphreys does, to use this, because you will save yourself a lot of trouble, and you'll things will be clarified if you use divided power notation. So dot. Okay. So what we want to say is, again for the same reason, these are all are linearly independent. For a similar reason, because they belong to different eigenspaces for H. Okay. And I know that, so we know y to the n equal to v equals 0 for some n. So let's do y x of v, or sorry, x y of v. Let's make a calculation. So this we see is right, and x of v is 0. Okay, so what does that give me? Right. Okay. Now I say, so there is a, so here is another exercise. Okay. Maybe I should be doing this, but I'm afraid if I start doing this on the board, I'll get incredibly messed up. It's very easy, but I don't trust myself to do this on the board. So I give this as an exercise. This is a simple induction. So this is the first step of the induction. So so x of v is 0. X acting on yv is lambda times v. So it's pushing it upwards with some coefficient in front. So the next thing I want to compute is x on this. It will be this times some factor which is an important, the coefficient in front is important. Okay? And the point is you have to compute that coefficient. Okay? So I claim that by induction you can prove the following, and here if you don't use divided powers, your formula will be extremely complicated. As we saw, if you use divided powers, exponentiation, the formula for exponentiation, the formula for binomial theorem, for example, they become very pretty and simple. Okay? So that's the advantage, and it continues to be an advantage here, is equal to lambda minus n plus 1, and this is a very important coefficient here. See, if you don't use divided power, so here you have an n factorial below, here you have an n minus 1 factorial below. So you will, the Humphreys will write it as x y to the n v is equal to n times lambda minus n plus 1. Yeah. But this has much better form. Okay, so I leave this as an exercise. It's an easy computation. Okay, but now we are done. We are at the end of. So suppose n is least such that y to the n v equal to 0. I know, sir, that such an n exists, right? So I should say something else. I am assuming v is non-zero and the highest weight vector is non-zero. Okay. So so highest weight vector, just like an eigenvector, by definition is a non-zero. Okay. Okay. So I know v is non-zero. Okay. Y of v could be 0. I don't know, but there is some n such that y to the n v is 0. That I know. So let n be least such that y to the n. So it could be 1, it could be higher. Okay. But then if I plug that in, what do I get here? I get that this is non-zero. This is 0. So what does that mean? This coefficient in front must be 0. Okay? Which means that this lambda must be equal to n minus 1. Okay? So we get then lambda is equal to n minus 1. In particular, lambda is an integer. See, that's a very strong condition. The eigenvalues for H must be integers now. This lambda was an eigenvalue for this V. That must be an integer. That's what we have concluded. Okay? Lambda is an integer and n is equal to lambda plus 1, which means if I chose I have V, y square V, y to the n minus 1 V, and there it should stop there, and the next one is 0. Okay? So this n is determined by this eigenvalue lambda. That's what we have shown. Okay? Now, there you go. Now we are done. So look at the span of, notice that the span of V, y square V, y to the n minus 1 V is SL2 invariant. There are eigenvectors for H. The H doesn't move them. What does X do? This formula says X moves them backwards and forwards. Y, of course, moves them backwards and forwards, but we know how Y acts. That's what. So the conclusion is if V is irreducible, so I say we are done. We have proved the theorem. Okay, we just have to convince ourselves that we have proved it. Okay, so if V is irreducible, then what can you do? You choose a highest weight vector, it exists, and then those things there. So there was this lambda, which was the eigenvalue for H of that highest weight vector, and then there was this n. This n must be equal to lambda plus 1, and these must be the other vectors in your. Okay. In particular, the dimension is n, n, which is lambda plus 1. That was dimension of V sub lambda is equal to lambda plus 1. We have proved that. And further, the highest weight here, which means this is called the highest weight. The reason for calling this the highest weight is this is lambda minus 2, this is lambda minus 4, and this is minus lambda. Okay. So is SL2 invariant. Okay, so finally let me write. So any irreducible SL2 module is determined by the weight of a highest weight vector. So if you have an SL2 module, any irreducible SL2 module, if it has a highest weight, if the highest weight is something, the weight is, it must be an integer, and if it is 10, then if you have two modules which give you highest weight vectors with weight 10, they must be isomorphic for. So if W in W and V in V, so this is irreducible, are highest weight vectors of the same weight lambda, then we know that W is V y square V y to the n minus 1 V, and W is W y square W and so on. V is V y V and so on. And if you map y to the n or j W to y to the j V, this is an isomorphism. because you can just check that the actions of H and X and Y match. Okay? So we've proved the thing. Okay? And this is a baby version of all the theorems, or not, I could say all the theorems, but maybe to be safe, I'll say most of the theorems at least for the course. Okay? Okay, now in the remaining few minutes, I'll talk about characters. Okay? And so you okay, so I'll maybe I'll say, since I seem to have some time on hand, I will say a few things about roots and weights. So, so you were introduced to root systems this morning. Okay? That seems to be an entirely different subject altogether, right? I mean, there was no Lie algebras anywhere. But the reason root systems are important is that they classify, they are a parameterizing set for semisimple Lie algebras. There is a one-to-one correspondence between complex semisimple Lie algebras and root systems. That's the reason root systems are being studied. Okay? Now, roots, there are also, I mean, it's not just complex semisimple Lie algebras, but there are several other classification problems which seem to have the same answer. And I think it still remains a mystery as to why many of these seemingly different classification problems should finally have the same answer. Okay? But be that as it may, so one of the things we will do is, if we are going to understand this classification of semisimple Lie algebras by means of root systems, then we would have to do two things. We would have to, among the things which we will have to do is attach a root system to a, given a complex semisimple Lie algebra, I have to attach a root system. Okay? How am I going to, so so you saw in the morning that the root system consisted of a vector space and a certain finite set of vectors in it. Okay? Where is this going to come from? You can ask. Okay? So, so there is a subalgebra, or a choice of you make a choice of a certain subalgebra called a Cartan subalgebra. Of the semisimple Lie algebra. Okay? Let me tell you what, of course, this is a choice. There are many Cartan subalgebras, and you fix a choice. Okay? In our case, the good choice is this is a choice of a Cartan subalgebra. This one-dimensional space spanned by H. More generally, if you are in SLN, which is the Lie algebra of n cross n traceless matrices, then the diagonal subalgebra will be a choice of Cartan subalgebra. Okay? So, this will be diagonal traceless matrices. So, diagonal subalgebra, yeah, diagonal traceless. Yeah? So, this is a choice of a Cartan subalgebra. Then what do you do? What you do is start analyzing the adjoint representation. Okay? and the theorem will be by the preservation of Jordan decomposition. What you will know is that, see, these, and it's a good check. See, here H, the action, what is the adjoint action of H? It acts on x, y, and x, h and y are eigenvectors for the adjoint action, right? And x has eigenvalue 2, y has eigenvalue -2, h has eigenvalue 0. Okay. So, if you look at elements here and analyze the adjoint action, you will see, for example, here is something you can work out. So, Eij, you take the matrix Eij where I is not equal to j, meaning zeros everywhere except at the ijth position. This is an element in here, right? Okay. Now I claim for the adjoint action of the diagonal subalgebra, this is a common eigenvector. So I say D of this, where D belongs to the, or H more appropriately, H is in the diagonal subalgebra. So let's call this H because that's the notation for the Cartan subalgebra. What should this be? This is so you will see that this is H sub I minus H sub jj times Eij. That's an easy calculation. In the dual of, so what is this element? This element sends, so this element here sends H to Hii minus Hjj. It is the linear functional which takes a diagonal element to the ith entry minus the jth entry. That's a linear functional. Okay? As a linear function, it lives in H star. Okay? Now, you take the set of all, so now this is a finite set. What you will see is that your Lie algebra will be decomposed. So you will see that SLN is equal to diagonal subalgebra. So that's H direct sum as a vector space Eij I not equal to j. Right? This is just vector space as vector spaces. Now these are okay. So you will get a finite set of elements which will live in H star. So the vector space in which the root system lives is H star, and the vectors are precisely the elements of H star which appear as eigenvalues in this decomposition. Okay? So for example, for SL2, what is the root system? The corresponding root system, you take the dual of this space. H is a one-dimensional complex vector space. Its dual is also a one-dimensional complex vector space. So I draw a line. Each point on that line represents a linear functional on the on H, on the space spanned by H. But I can represent, if I take some vector here, lambda say, lambda represents the linear function which is lambda on H. It's a natural thing to, so H star again is I represent by a line, complex numbers, and the roots are 2 and minus 2 because X, the eigenspaces here, the values are 2 and minus 2. So that's 2 here and minus 2. So you saw this in the morning that this was a root system of type A1. Okay? Now that happens very generally, and I urge you to draw the root system for SL3 using this and see that actually it is this picture that was drawn on the okay. But this picture you will see if you stare at a three-dimensional XYZ axis along the line x equals y equals z. Did I say that correctly? So this is if you, so there is this plane where the coefficients of x, y, z are the sum of the coefficients is 0. Okay, take that plane in 3-dimensional space and turn it so that you are staring at it orthogonally. Okay, and if you see that, the roots will look like that. If you stare along a 3-dimensional space, turn it around so that this plane that is, if you are looking down, the horizontal plane is the plane where the sum of the coordinates of x and y and z are 0. And so these roots are, remember, live in 3-dimensional space, because h is sort of you're looking at h1, h2, there is 1, 2, 3 coordinates, if you wish. So maybe I'm getting ahead of myself. Huh?
But C3.
Yeah, in C3, if you think like that, this will be okay. Maybe I didn't think about this. I just started saying this. So maybe but what I'm saying is correct. But maybe I'm not saying it the right way. But maybe we should go on. Okay. So so let's go. So not only. Okay, now let's move from the adjoint representation to a general representation. Suppose I have a representation V of a semisimple Lie algebra. Okay, I take this diagonal subalgebra. I know that for the adjoint action it acts semisimply, that is, it is diagonalizable. So for any representation, by the preservation of Jordan decomposition, these elements will act semisimply. Okay, so given a vector space, given a representation V, I can decompose it into, so given a representation V, so this is a G semisimple and G acts on V, this is finite dimensional. I can decompose it into eigenspaces, common eigenspaces for the action of H. So V lambda, where V lambda is given the following definition, is V in V such that H, so lambda is in H star. Okay, here only finitely many are non-zero. H of V is equal to lambda H of V. Okay, you can write that. And these are called the
For all H in
script H star. For all H, yeah, sorry, yeah, you're right. Yes. Okay, so if you write, so let's review. If you write the adjoint representation itself, the elements that you see here of H star, those are the roots. Those are what we said. So this is the, in particular for the adjoint representation, I have written it like this. Of course, okay, I should correct myself. There is the 0 part, which is this Cartan subalgebra part, and there are some non-zero eigen lambdas, and the non-zero ones are the roots. Okay, but this is true in general. Okay, and what I can do is attach to this vector space V the following element. So I take the dimension of V lambda, put a formal symbol exponential and of lambda and sum over so call this the character of V. Okay, formally this lives in, okay, maybe I'll, before I say let me write out. So this is just a formal symbol. Okay. So for example, let's write out the character of PD or V lambda for so take G is equal to SL2, V is equal to irreducible. You know what PD is, right? Yeah, so let us write out the character of PD. What will it be? It will be, I have to take PD and decompose it into eigenspaces for the action of the Cartan subalgebra. Here the Cartan subalgebra is just the single element H, spanned by the single element H. So I decompose it. So PD, it was all polynomials of degree D. What are these? These would be u to the D, u to the D minus 1 V, V to the D. Okay? What is the eigenvalue here? H was u del by del u minus V del by del V. So the eigenvalue here is D. The eigenvalue here is D minus 2. The eigenvalue here is minus D. So what should I write for the character? I should write e to the D and write, or x to the D, e or x. I also written, this can also be written e to the lambda. Okay? E to the D, and here I write the dimension, which is 1, right? Plus e to the D minus 2 plus dot 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 plus e minus D. That's the character. So where does this live? This lives actually in Z, in the group ring. So you understand the group ring, right? So you've all seen what a group ring means. Now, if I take the complex numbers, additive group of complex numbers, think of it multiplicatively. If I want to write an additive group multiplicatively, what do? I write, that's the reason for writing that exponential. I write exponential of group elements, right? So this lives in the group ring with integral coefficients of the group complex, of the complex additional, complex numbers with respect to addition, but written multiplicatively. Okay? So this corresponds to the element D, the complex number D, which you have written e to the D. And the coefficient in front is an integer. Actually, you may say it belongs to N, not just to Z, group ring, but the group semigroup ring. Okay? So this is complex number is additive group. Yes, complex number is additive group, but you are writing it, you want to make it a multiplicative group, you want to write it multiplicatively, so you use the exponential notation. Okay? Now the thing is, so we attach this, call this the character. Okay? And the point is, you see the characters are, you can write down the character of a representation, and you will see that if you do the exercises that I will now assign you, you will see immediately how you can use characters to decompose a given representation into irreducibles, just like you do for finite groups. Okay? So let me, I'm out of time, so let me just finish by giving you a few more exercises. So these are out of Humphreys, tutorial sheet 2. So Humphreys, so 7.1, 7.2, 7.6. Okay, in addition to whatever I've assigned now, and let me put some comments in front of them. I call this T, C, CI, where T stands for theoretical, C for computational, I for important. Okay. So see you tomorrow at 9:15. Okay.